In the following lecture, we're going to discuss how we're going to figure out the pH of a solution and what is meant by the term pH. Previously we discussed what water constant was. I told you that water ionizes very weakly, very extremely weakly, and ends up producing H plus 1 and OH minus 1 ions, and there's a reversible reaction whenever you have water. The concentration of H plus 1 and OH minus 1 ion is very low under standard conditions. It's 1 into 10 is per minus 7 mole per decimeter cube. And similarly, the concentration of OH minus 1 is also extremely low. It's 1 into 10 raised to the power minus 7 mole per decimeter cube. The reason the concentrations are equal is that when water dissociates, the same amount of H plus 1 and OH minus 1 ions are produced. Then we also derived the expression for Kw, which was the water constant, which is basically the equilibrium constant for this expression. It's the concentration of H plus 1 ions into the concentration of OH minus 1 ions. So my products are H plus 1 and OH minus 1. And it was divided by the concentration of water. But since water was in excess, so its concentration is probably going to be a constant, or there would be negligible change. So we take that as a constant. So our expression for Kw was only H plus 1 concentration multiplied by OH minus 1 concentration, and the product came out to be 1 into 10 raised to the power minus 14 mole squared dm minus 6 was the unit for the expression. And this remains a constant. The only thing that changes the value of this constant is temperature. So only changes with temperature, and I've also written that this value is obtained under standard conditions, 25 degrees centigrade and 1 atmosphere. So changing pressure or changing any other condition would have no effect on this value except for changing temperature. Another important thing that we have previously discussed is that if you look at this equilibrium carefully, this equilibrium is established in water. If you add acid to water, if there's an aqueous acid, acids are proton donors, or they produce H plus 1 ions. So if they produce H plus 1 ions, the quantity of H plus 1 or the concentration of H plus 1 would increase. Vice versa, acids neutralize OH ions, so the quantity of OH ions or concentration of OH ions would decrease. So H plus 1 concentration increases, OH minus 1 concentration decreases, but the value of the equilibrium constant Kw would remain exactly the same, because one of the terms would increase and the other term would decrease, but the product would still remain exactly equal to 1 into 10 to the power minus 14 under standard conditions. So adding an acid to water would have no effect on the equilibrium constant or the water constant. In a similar way, adding a base or an alkali to water would decrease the quantity of H plus 1 ions, because bases are proton acceptors. So they decrease the quantity of H plus 1 ions, and the quantity of OH ions or the concentration of OH ions would increase. So adding a base, concentration of H plus 1 goes down, and the concentration of OH ions vice versa would increase. So if you look at the value of Kw, H plus 1 decreases, OH minus 1 increases, but the product of the two would still remain equal to 1 into 10 to the power minus 14. So adding a base or an acid would have no effect whatsoever on the value of Kw. Now the next thing that I'm going to do is I'm going to take the log of the expression for Kw. This is my expression for Kw. The value is 1 into 10 to the power minus 14 under standard conditions. I'm going to take the log of Kw on both sides. So taking log, if I take a log, and this is base 10 log, so my expression will become log of Kw, which should be equal to the log of the concentration of H plus 1 into the concentration of OH minus 1. Remember, when you take the log of a product, after the log, it becomes log of H plus 1 plus log of OH minus 1. So this expression would change into log of the concentration of H plus 1 plus log of the concentration of OH minus 1. And finally, I'm also going to take the log of 1 into 10 raised to the power minus 14. If I take the log of 1 into 10 raised to the power minus 14, I get minus 14. So this would be the value that you will get if you take the log of 1 into 10 raised to the power minus 14. So I've taken the log of this entire expression of Kw, and I get this expression over here. Another thing that I'm going to do is, and I'm going to explain that later, is I'm going to multiply everything by a minus 1. So this would become minus. This would become minus log of h plus 1. Let's rub this sign off, because this would also become minus log of oh minus 1. And this value over here is going to become plus. So this over here is the expression that I get when I take the log of this kW, water constant. This is my expression. And this value, if I simplify it further, remember this, that this thing over here, minus log of h plus 1, is called pH. So this is my pH. And this thing over here, minus log of OH minus 1, or the log of the concentration of OH minus 1, is known as POH. So this is POH. And the sum of pH and POH should be equal to plus 14. So pH over here stands for the minus log of concentration of H plus 1. POH on the other hand stands for minus log of the concentration of OH minus 1. Remember, the term P generally stands for minus log. You put P if you want to take the minus negative log of something. So let's highlight our second version of the same kW water constant, which is this thing over here. So remember our kW, which we have mentioned over here at the top. kW is the concentration of H plus 1 into the concentration of OH minus 1, and it has this value over here. And if you take the minus log of everything in kW, you get this expression, which is pH plus POH is equal to 14. So this is how the term pH is derived. And remember, pH is the concentration, log of the concentration of H plus 1 with a negative sign. I would also like to remind you why this term pH, or why the concentration of H plus 1 is so important to us. As I've told you that there are three types of conditions. Remember, all reactions on Earth, or most of the reactions on Earth, the main solvent is water. And water plays a very important part in most of the reactions that are happening, whether they are biological reactions, plants and trees and human body, etc. Most of the time the solvent is just pure water. So water can be in three conditions. It could either be acidic, where the concentration of H plus 1 is greater than the concentration of OH minus 1. It could be basic, where the concentration of H plus 1 is lesser compared to the concentration of OH minus 1. Or it could be neutral, where the concentration of H plus 1 and the concentration of OH minus 1 are equal. So it's very important for us we follow or we measure the concentration of H plus 1, because different reactions need different concentration of H plus 1. Some require acidic medium. For example, the reactions, the digestion reactions in the stomach, your stomach has an acidic pH. So all the reactions that are happening in the stomach or in the intestines, they need acidic conditions. So the concentration of H plus 1 must be greater, which means that there's an acid present which is producing H plus 1 ions. In other areas, some reactions would require alkaline conditions, so the concentration of OH minus 1 would be greater. Whereas a lot of reactions require neutral conditions, so the concentration of H plus 1 and OH minus 1 must be equal. So different reactions need different amounts of H plus 1. So it's very important that we know the concentration of H plus 1, whether it's high or whether it's low. But then what's the purpose of taking the negative log of that? Why don't we just follow the concentration of H plus 1? Whenever we are given a solution, why don't we simply measure the concentration of H plus 1? Why do we need to take the log? What's the purpose of taking log anywhere? Now, the reason why log is important is because it scales the value. It expresses those values in the powers of 10. We are talking about base 10 log. So it expresses those values in the powers of 10. For example, the H plus 1 concentration in your solution could vary drastically. It could be extremely low. For example, it could be 0.00001, or it could be relatively high, which means that the concentration is 0.1 mole per decimeter cube. So the concentration in your solution or during a reaction, it could drastically vary. Now, if you look at the two values, there's a huge difference in the two values. One is very, very small and the other one is relatively larger. if I take the log of both values, so taking the log of both and taking the negative log, so you can use your calculators, you take the negative log of 0.0001 and you take the negative log of 0.1. This value is going to be equal to 1, whereas this other value would be equal to, it's going to be 1, 2, 3, 4 and 5. So your answer is going to come out to equal to 5. Now you can notice that the values have been scaled. If you take the function of log, 0.001 was a very small value. The real problem that you're going to face is if you're plotting a graph. Plotting 0.1 and 0.0001 concentration on the same graph is going to be very difficult, because it would be very difficult to choose a scale that would fit the two values. But if you take the log, your values automatically scale up. 0.1, log of 0.1 is 1, log of 0.0001 is 5. Plotting 1 and 5 on a graph paper is very easy. So if you're making a graph and you're trying to figure out the concentration of H plus 1, the concentration of H plus 1 could vary drastically. It could be very high or it could be extremely low. So if you scale up the values by taking log and expressing them in terms of the powers of 10, your values become closer to whole numbers and plotting them on a graph becomes easier. So now by looking at the graph, you can figure out whether the H plus 1 concentration is low or the H plus 1 concentration is high. This is the reason, this is the main reason why you take the log, because it becomes easier for you to plot graphs. So we always make graphs using pH or the pH scale. We don't plot the values of H plus 1 concentration because plotting them becomes extremely difficult. One other very important thing about taking minus log is that minus log, if you take minus log of anything, it's going to convert smaller values and change them into bigger values and vice versa. For example, when we were taking the minus log of the concentration of H plus 1, this was a very small value, but taking the minus log, our value actually came out to be bigger. Vice versa, the concentration of 0.1 was the larger value, but when we took the negative log of that, we got a smaller value. So smaller values, you take the minus log, you get a bigger value. You have a bigger value, take the minus log, you get a smaller value. So remember this, that the values get inverted if you take minus log. Bigger values come out to be smaller, smaller values come out to be bigger. So whenever you see that the pH is coming out to be low, that basically indicates that the concentration of H plus 1 is higher. It's the opposite. And whenever you see the pH or minus log of H is coming out to be high, that means that the concentration of H plus 1 is actually lower. So pH low means that the solution is acidic or has more H plus 1 concentration. pH high means that the concentration of H plus 1 is actually lower and the solution is more basic or more alkaline.